Two positive charges Q and 4Q are a distance L away, as shown in the following figure here. A third charge is introduced near the two charges so that the three-charge system is at equilibrium. What kind of charge should be introduced, and where should the third charge be placed? So, we look at this. This diagram shows kind of where they are. So if I redraw this here, this is Q, this is 4Q. We need to place some sort of charge in the middle to balance them out. So if you remember, two positive charges, these are going to repel each other. So you need a charge that will balance that repulsion and force them to actually come back to each other, be like more attracted to each other. And so a negative charge is the kind of charge that we would need, since the positive charges will both be attracted to this negative charge here. So a negative charge will be introduced, and we will need to figure out the magnitude and where this charge will be placed. So to do that, if you think about this diagram, these two are the two positive charges, and this is the length L. If we place a negative charge somewhere along the middle, there is going to be a distance between both of them. And it's not going to be in the middle, since the magnitudes of the two positive charges are actually different. So let's call the length from the negative charge to the positive charge Q. Let's call this distance x. Now the other one is the distance from the negative charge to the charged particle with a charge of 4Q. Let's call that L minus x. So if this is x, that will be L minus x, since that's the rest of the distance L. So we know that the forces that these two exert must be equal to the forces that the other two exert on each other. That is to keep everything balanced so that this charge does not get pulled one way or the other. So you can say that the first force, which is equal to K, and I'm going to call the negative charge Q, and this will be the magnitude of the charge. I don't actually want to bring signs into this to keep it simpler. We can add the negative sign at the very end, and that divided by x squared, which is the distance from Q to the negative charge, that must be equal to F2, which is the force between the negative charge and charge 4Q. And that is equal to the Coulomb constant times Q times 4Q, which I should probably write the 4 in the front. 4KQQ divided by L minus x, and we're going to square that quantity. So if these two are equivalent, we can immediately look, and we see that the entire top of force 1 and most of it of force 2 gets canceled out because these are all the same units. So we can divide them both all out. So we eventually get that 1 over x squared, which is where x squared is the distance between minus the negative charge and plus q, is equal to 4 over L minus x squared. And then we simply just cross multiply to get 4x squared equals L minus x squared. And then we can square root both sides. So get that 2x is equal to L minus x. So then 3x equals L. And then x is equal to L over 3. So the charge should be placed at a distance L over 3 away from Q, and a distance 2L over 3, or 2/3 L, away from charge 4Q. So 1/3 of the distance L away from Q and 2/3 away from 4Q. So I am going to erase this, erase everything, and I'm going to write that down. So the charge will be 1/3 L away from plus Q, and 2/3 L away from plus 4q. So we figured out where the third charge should be placed. Now we actually need to figure out its magnitude. So to do that, we can say that the force of all the positive charges minus the force of all the negative charges must equal 0, since all of the three charges would be in equilibrium, so there is no acceleration or net force or anything. So if you think about this in Newton's second law, there is no acceleration of any of the charges. So in that case, the force of the positive charges is equal to the force of the negative charges. So the force of the positive charges is simply equal to the Coulomb constant times q times 4q. I'm just going to write this as 4k q squared, since you have q times 4q. We're going to divide that by the distance L squared and square that. And for the force of negative, do the same thing. So the Coulomb's constant. And for q, you can use either one. I'm going to use plus q because that is simpler. So you have q, that's the magnitude of the charge, is actually negative. We'll get to that later. And the distance, if you remember, the x distance, which we defined as the distance between the charge with, or the charged particle with charge plus q, positive q, and the negative charge was L over 3. So that over L over 3 squared is the force of the negative charge. And that's going to be the same on this side too, since they're both not moving and they're both in equilibrium. So because of this equation, we can substitute and set these two equal. Squared divided by L squared equals KQQ divided by L squared over 9. And now all we need to do is just solve that equation. So going back up here, k's cancel out, and then you get okay, L squareds also cancel out, and the 9 moves to the top. So 4q squared is equal to 9 q. And the L squareds cancel out since you can multiply both sides by L squared. And now we just need to solve for the magnitude of the negative charge, which is capital Q. So we get that 9 times the magnitude of the negative charge is equal to 4 times Q. So Q is equal to 4Q divided by 9. So that is the magnitude of the negative charge. But the negative charge is actually negative, so Q will actually be minus 4Q, for little q, divided by 9, since it will have a negative charge to keep the positive charges from flying apart. And that is how you would solve this problem here.